Hello everyone, welcome back to Calculus PC. We're in lesson 25 where we're talking about differential equations. In the previous couple videos we've talked about how to solve differential equations and particular examples for those and using exponential growth and decay. And in this video we're going to talk about slope fields and how to visually look at what a differential equation actually truly represents. As you guys can see in the notes right here, it says the solution to a differential equation may be general or particular. And then particular is going to be where we give the initial condition. We've talked about this before. And there's three ways to solve differential equations. So we've talked about analytically. That was the first couple of videos. In this video, we're going to talk about it graphically. And then a little bit later on in a future lesson, we're going to talk about it numerically using Euler's method. So let's go ahead and talk about what it actually is. So if you're looking at a differential equation, which you're going to be given here, you're going to be given a coordinate plane and some points on the coordinate plane. What you simply have to do, and we're going to do an example here in a minute, to look at the differential equation, look at the point that you're given, and plug in. So if I were given the differential equation 2x minus 1, and want to know what's going on at the point 2, 2, I would plug 2 into my x value. Here, I don't have a y value, so it doesn't really matter. So I plug 2 in here, and I'm going to get 2 times 2 is 4, minus 1 is 3. So you guys can see at the point 2, 2, this slope, this mini little line right here, has a slope of 3, right? 3. So let's actually just go ahead and show you guys an example. All right, so we're going to go ahead and look at example number 2. It says give the differential equation dy dx equals 1 over x plus 3. We want to sketch the slope field. So one of the things about this example that I want you guys to notice is, again, there's no y value, just like down here there will be. So when we plug in for x, the y is independent. So let me actually talk about that for a second. So let's say that if I make x equal to, let's go negative 2 for a second. So I'm looking right here when x is equal to negative 2. So all of these values, all these points right here, x is going to be negative 2. Then I plug into my differential equation where x equals negative 2. I'm going to get 1 over negative 2 plus 3, which is going to give you 1. So I know that when x is negative 2, my differential equation is going to have a slope of 1. So I'm going to go ahead and I'm going to just go ahead and write a slope of 1. It doesn't have to be perfect by any means whatsoever, by any means at all. So just really honestly, we're looking for actually the fact that it's a slope that's positive. And then let's go and see what happens when x is equal to negative 1. So dy dx. So we're going to plug negative 1 into our function. And we're going to get 1 over negative 1 plus 3, which is going to give us 1/2. So we're going to get a little bit, oh, that one's a bad, that's a good example, but a little bit flatter, but still it's okay. Again, it doesn't have to be completely perfect. I'm going to change this one up just because it just looks a little too flat for me right now. But, it's just the same thing. And I did it again. This is where I should just completely edit it, but, it's fine. All right, there we go. So we're good with this problem. All right, let's keep going. So what happens when x is equal to 0? So dy dx is going to be equal to 1/3. Right, so just plugging in 0 here, I get 1/3. So we're going to get a little bit flatter, but still a little bit. Even though those look pretty horizontal to me, looking at them, but we're getting flatter. And we're going to do one more just so you guys can see the idea of what's going on here. So when x is equal to 1, we're going to get dy dx is going to be equal to 1/4. So the longer we go through this, the flatter these slopes are becoming, right? So they're not exactly, there's still a little bit of positive slope here, but not, completely. So just we're getting really, really small. All right, so let's go and we'll go one more on the other side of this. Well, what happens when I choose x equals negative 3? Well, when x equals negative 3, well, then my derivative, dy dx, is going to be undefined. Now, sometimes you're going to see that this is going to be completely left blank. What I like to see is the fact that all vertical lines have a undefined slope. So we have this right here. So this is the idea of what's going on. And if I choose something like, x equals negative 4, then my slope is going to be slightly negative. So if I do negative 4, it's going to be really slightly negative, like this. And so what you guys understand is that as we're moving throughout this, slope field, if we were to keep doing this, then as I move further away, or getting, closer to positive infinity, that these slopes are going to essentially get pretty much closer to 0, right? We're going to get smaller and smaller numbers. But again, they're all going to be slightly positive slopes. So this is the visualization for this differential equation. So what I want to do is this. Well, what does this mean? What does this represent? Like, what are we doing here? So let me show you guys something really fast. Okay, so I went ahead and erased this thing right here. I'm going to go ahead and solve this differential equation. I actually want to look at it really quickly. So we're going to, and this is not, this is not asking us to solve it, but I need for you guys to understand what this is representing versus like what this is, why we care about this. So we're going to go ahead and solve this differential equation by separating variables, and we're going to integrate both sides. And so the integration of 1 is going to be y, and then the integration of 1 over x plus 3 will be the natural log of x plus 3. We would do u sub here if we need to do that, plus some value c. Well, guys, I want you to look at this graph, and I want you to think about this for a second. So let me do one more quick thing off camera. Okay, so I went ahead and put on my graphing calculator y equals the natural log of x plus 3. And if we were to graph this, and look at the behavior of this graph. Look at the behavior of this graph, and I want you guys to see this by looking over here. Well, if I chose a random point, let's say we actually were looking for a particular solution, and let's say we chose the point, let's just say 0, 1. So we look at 0, 1. So we're right here at this point 0, 1. And so slope fields basically say, so we're now changing the problem up a little bit and asking about this. So if I ask you guys to create a solution, draw a solution, given the point that 0, 1 is a solution to this, I always tell students, like, slope fields are kind of like, an idea of what's to do. It's kind of like we're kind of blowing in the wind here, and this is telling us the direction that we're headed in. So this is saying that we're going to get flat, flat, flat as we go this way. So we're going to start getting steeper and steeper, steeper to 0. And this is going to say that we're going to get, a little bit less steep, and then really steep, and then we're going to just essentially go right here. We cannot cross this as a brick wall. So this is a very poorly drawn picture of this. But you guys can see that if you follow the slope field given this point and go back to what we just saw here, right, they are the same graph. So solving the differential equation gives us, and graphing the slope field gives us the behavior of our graph, our f of x graph, once we get it. So I think that's actually a really cool thing to see with these particular example, that you can see that just graphing simple slope fields gives you, again, a visual representation of what the solution to the differential equation is going to give you. So that's why we do that. Okay, so now let's go ahead and look at example number 3. So this one we have an x and a y. So for this particular example, ladies and gentlemen, we can first of all say, okay, what happens when x equals 0? And so you do the same thing, but this now we got to take into a point. Well, when x equals 0, so when x equals 0 right here, then our slope field is going to be, so when x is equal to 0, well, what happens when y, and this is where definitely charts are going to come into play. So y is going to be equal to our dy dx. All right, so when x is equal to 0, then y is going to be equal to dy dx, because this is in 0. So when y is equal to 0, which is right here, then my derivative is going to be equal to 0. When y equals 1, my derivative is going to be positive 1, so a little bit bigger. When y equals 2, my slope field, my dy dx is going to be positive 2, and then 3. So we're going to get a little bit steeper as we go up our line here. When y is negative 1, it's going to be negative 1, right? They're just equal to each other. Y equals negative 2, negative 2, and then negative 3. So that's a really easy way of seeing those two, this axis. Well, you can go the other way with this and say, well, what happens when y equals 0? When y equals 0, x is going to be equal to dy dx. So we're going to plug 0 in here. So when x is equal to 1, when x equals 1, dy dx is equal to 1, 2, 3, 4. So whatever x is, dy dx is. So our little mini slopes are going to be indicated of this. And again, guys, notice I'm not being perfect here, right? They're all positive. They essentially should have a little bit more of a steeper slope, but, it is kind of what it is. So I don't want you guys to waste very much time at all trying to do this. Like, this kind of looks like the same to me. But again, it is, supposed to be a little bit steeper as we move along. All right, so let's choose. So those were pretty easy to do. So let's go into actual points now. Now, you're not going to have to solve every single one of these points. It would take too much time. So what I want to do is I want to choose random points in each quadrant so we can look at it. And then you can also see the kind of behavior that happens as we move up and down, our axis. So let's go ahead and do simply 1, 1. So if x is equal to 1, so instead of actually doing x equals 1, y equals 1, let's just actually look at the point. So if I'm looking at the point 1, 1, then dy dx is going to be equal to 2, right? 1 plus 1 is going to be 2. So at the point 1, 1, this slope is going to be equal to positive 2. And again, really all I'm going to care about is that you show me a positive line here. It's not horizontal, it's not vertical, it's not negative, it's positive. If I were to go and plug in the point 1, 2, right? So 1, 2, this point right here, then my dy dx is going to be equal to 3. So then I'll be a little bit steeper. And then this is going to be 1, 3. This is going to be 4, right? So it's going to be a little bit steeper. Well, what about negative 1? If I do negative 1, 1. Well, if I add these up, this is going to end up being 0, right? That's going to end up being 0. So now this is where I go to another selling point. Well, what happens? What can I do to make dy dx equal to 0? So dy dx will be equal to 0 when x is equal to negative y. Right? If I make this equal to 0 and I solve for this, I can say that x will be equal to negative y, or y equals negative x. It doesn't matter. So the line, so actually let's do it that way. So y equals negative x. So the line y equals negative x is what you guys see right here. So everywhere there's a point. So again, when x equals 2, y equals negative 2, that's going to end up being 0. So you can very easily solve some of these points by just doing this as 0. And the other thing that's really cool about slope fields, guys, is that there's usually always a pattern here. So let's go now look at 1, negative 2. 1, negative 2. Well, again, we're just adding these two numbers up, right? That's what the differential equation says, is that I just add x and y together. So this is going to give me negative 1. So this is going to be negative 1, so a negative slope. And then here, if I go and do 1, negative 3, like 1, negative 3, that's going to give me a negative 2 slope. So notice that over here, I'm above the x-axis, I'm positive. Here, I'm going to be negative for this line. Now, you want to do a couple more to make sure that this actually, works with what's going on. So if I choose something like 2, negative 1, that's going to give me a positive slope. If I go and do something like 3, negative 1, that's going to be a positive slope as well, and then also a positive slope. If I go to 3, 2, this is also going to give me a positive slope because my x value is greater than my y value. The positive number is greater than my negative number. And the same thing right here, right? This is going to be 4, 2, and this is going to be 4, 3, negative 3. And, so I know that these are all going to be positive slope. These are always going to be positive, right? These are always going to be positive because both x and y are both positive. So yes, they are going to get steeper as I move up, right? This would be, if this is 4, 1, then this slope would be 5, this slope would be 6, and this slope would be 7. But again, we're just looking at our slopes. If this is going too fast for you guys, you can literally go and put these numbers in here. In here, this is negative 1, but this is positive 2. So again, my positive number is bigger. This is going to be positive, positive. Now on the flip side of this, if we go and look at negative 1, well again, negative 1 is going to be a negative 2, right? So this is going to be a negative. And so everything that I'm doing now, my negative value is actually bigger than my, in quadrant number 3, they're both negative. So that's kind of, obviously, they're all going to be negative. But here, if I go negative 2, positive 1, the negative value is bigger than the positive value. So this is going to be an easy way. Again, you're not going to have to do this for everything, but you guys get to see that this is how you're able to graph this slope field in a very fast way. And again, if you have no idea what you want to do, let's go back really fast and say what's going on at the point negative 3, positive 1. So negative 3, positive 1. Well, you can literally plug in negative 3 plus 1 and get the slope of negative 2 and then draw the slope of negative 2 here. So that's really what you have to do. But again, slope fields, you have patterns, but mostly you will just have to plug in at the most, I think, 9 points. 9 points. And usually patterns will help you out. So that's going to be this video for slope fields. We'll come back in the next video where we do some more practice, and I'll show you guys how to differentiate different slope fields. So I'll see you guys in the next video.